Okay, Giant team members. In this video lecture, we're taking it a little one step farther each time we have these videos about what we can do and what type of problems we can examine and how we could go about answering questions in a more quantitative way and using the data that we collect to develop some kind of confidence in our answers. And that's why right now we're going to be working on confidence intervals. So confidence intervals defined is a range of values constructed from sample data, okay? Constructed from sample data. Make sure we know that. So that the population parameter is likely to occur within that range at a specified probability. So whatever parameter, whatever thing we're looking at, to try to predict, to try to determine from the population, and usually it's the average or the mean that we're trying to predict, but we want to take a sample and we want to say whatever population parameter we're looking at, we want to make sure that it falls within this range, this interval of what we determined, right? So and we'll get to an example of what exactly we're trying to do. And I don't want to get too far ahead of you here, but we're taking sample data. And from that sample data, we're trying to determine a population parameter within a certain range, right? Within a certain range. So if we're saying, if we go back to customer wait times, we might say we're going to take a sample and we want to be pretty confident that that sample of wait times really represents what the actual wait time is for the population. And maybe we come up with 4.5 minutes to 5.5 minutes. And then we could say, look, we're confident within this degree, we have this much confidence that the average wait time for customers for the population will fall somewhere between those two times based on that sample that we took. So again, to summarize, we're taking a sample, we're trying to represent something from the population with a certain level of confidence so that when our boss asks us, how sure are you, how likely is this to happen, we could say we're 95% confident. The specified probability, spell that wrong. The specified probability is called the level of confidence. So we're going to say, when we answer these questions, we're not going to say, yeah, the wait time for the customer is between this and this. We're going to say we're 95% confident. We're 90% confident. We're 90 whatever percent confident that the wait times fall between these two numbers for the population based on the sample that we took. And these are typical levels of confidence, 99, 95, and 90. Now, for most research being conducted in industry or something along those lines, 90 is typically good enough, right? You don't need to be 99% sure. Now, 99% sure is appropriate if you're doing medical research or you're testing drugs or the impact of new drugs. Then you want to be really, really sure about your results. So you want to use something like a 99% confidence level or a confidence interval. For most daily applications, 90. I think they use 90 for election polling results and things like that. So, they'll always say, here's the results plus or minus 4 points or 5 points, because there is always going to be error. For our purposes, for this class, being that we don't have a lot of time, I think we're just going to be using 95% confidence levels for just about everything we do. It's nice. It's right in the middle. It'll be easy to remember. So I'll show you how to compute the confidence interval, but for our purposes, we're going to be using 95%. And here's the formula that we use for our confidence interval. And let me go through each one of those to make sure that you understand what we're talking about as we look at this equation. The first thing we have is X bar, right? And that's the average that's coming from our sample data. Okay, so we know there's a lot of it. We have a lot of information, but we're going to pull a sample and we're going to use that sample mean as kind of our starting point. And then we have plus or minus, plus or minus. So we're going to add something to this mean, and then we're going to subtract something from the mean. And when we add it and subtract it, we're going to have two numbers, and that's our interval. That's our range. That's our, our confidence interval are those two numbers. So the sample mean plus or minus our z-score. Now our z-score is going to be coming from the level of confidence that we have. So I'll show you how to calculate this. That's coming from the level of confidence times our population standard deviation. Okay, so we have the population standard deviation is known in this example that I'm giving you. There are going to be times when we don't know the population standard deviation, right? So if I'm a company and I'm in business for many years and I've collected mountains and mountains of data, I'm going to know what the population standard deviation is. And then as I pull samples in my daily operations, I could use that population standard deviation because it's going to give me a really better accurate indication of what the process variation is. In future videos, we're going to do a formula where we don't know the population standard deviation. Okay, so in this instance, we know the population standard deviation. We're going to take that and we're going to divide it by the square root of whatever our sample size is. Okay, so and this part right here, if you were to take this just by itself, this represents what we talked about earlier, the error that's inherent when we sample. And the bigger number we get for a sample size, the smaller that our error is going to be. The smaller our standard deviation, the smaller our error is going to be. So, if we have this information from the population, the standard deviation, we want to make sure we use this formula, okay? And I'll show you how to fill it in and all of that. Before we get to the problem itself, let's go ahead and understand where this Z number comes from, where this Z statistic comes from based upon our confidence levels here. And I just want to make sure we know that we are dealing here, that these guys are coming, this Z number is coming from our level of confidence. And we said we want to use a 95% level of confidence. Okay, so let's pretend this is our interval. The two red lines represent our intervals, and we want to be 95% sure that the numbers that are here and here represent that those two numbers contain, that's a better number, word, contain our population mean, okay? So I get a number, I put it here, I get a number, I put it here. I want to be 95% sure that our population mean is somewhere in there. It could be here, 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 but it's somewhere between those two numbers. What's bad is if my population mean is actually here, or here, or here, outside of what my confidence interval is. So that's why we set a confidence interval at what we do. If I were to set this at 99%, these red lines would be moved out even more, and it would be harder for me to not have my population mean within that interval of where it is, okay? With 90%, it would actually be a little tighter, and there's a greater chance that my actual population mean is going to be outside of that interval, okay? So that's what we're really trying to do. We're trying to predict what the population mean is by coming up with some parameter, I'm sorry, it's a bad word, by coming up with some range that will contain the population mean. Okay, so we're using 95%. So if I take this area under the curve between the two red lines, that has to be 95%. Okay, that has to be 95%. So being the brilliant mathematician that I am, I know that this side of the curve, I know that this side of the curve here has to be 0.47, I'm just not getting my numbers to come up. it has to be 0.475, okay? And I also know this side of the curve has to be 0.475. Because 475 and 0.475 added together equal 95%. And so this area under the curve is 95%. Okay, but that doesn't tell us our Z statistic, right? You're probably saying, nope, that's not the Z statistic. That's the area under the curve. We were using the Z statistic to determine the area under the curve before. So now what do we do? Well, we just go back to our Z table that we're using before, and we have to find 0.475 in here somewhere. Okay, so we see that 0.475, I just lost it. There he is right there. So that's the area under the curve. Well, what numbers does that represent? It represents 1.96. So if I go down here, over here, 1.9, that intersects there at 47.5%, 1.96. So I know then that my Z here is 1.96. Whenever I use a 95% confidence interval level, my Z is going to be 1.96. And we could do that for 90% and 99%, right? This would be 45 and 45 if I was using 90%. So I would just go in here and find 45%. It's between two numbers, actually, so it would be 1.645. You see how it falls between here somewhere? So it would be 1.645. And you could use 1.65 or 1.64. It doesn't, you're talking just tiny amounts of error there. So, and then the same way with 99, you would just do that and look at it that way. So we have one part of this problem right off the bat when we're using 95% confidence level. So that's what we're gonna use for our example. So let's go ahead and go through this sample problem. We'll fill in the data, and then we'll calculate what our intervals are, and then I'll tell you how you state that, how you say, here's what it is, okay, in a very statistical way. So Del Monte Foods, which you're probably all familiar with, distributes diced peaches in 4-ounce plastic cups. They're delicious. I eat them and my son eats them. To ensure that each cup contains at least the required amount, Del Monte sets the filling operation to dispense 4.01 ounces of peaches in gel in each cup. And that makes sense, right? They don't want to give the customer less than 4 ounces. They're trying not to give the customer less. So they're going to fill it a little bit more. They're not going to fill it a crazy amount because they don't want to waste product and spend a lot of money. So they're going to set the filling stations at 4.01 ounces of peaches and gel. Of course, not every cup will contain exactly 4.01 ounces. That's why we have quality departments. Some cups will have more, others will have less. From historical data, Del Monte knows that 0.04 ounces is the standard deviation of the filling process, and that the amount follows a normal probability distribution. Okay. It tells us a lot of information. We have historical data. We have the population standard deviation represented here, 0.04. So we know we're going to use this formula. We know we're going to use this formula. And it's normally distributed. So great. We could use our Z, and okay, that just confirms what we could do. The quality control technician selects a sample of 64 cups, okay, at the start of each shift, measures the amount in each cup, computes the mean fill amount, and then develops a 95% confident interval for the population mean. Okay, again, a lot of information. Every morning, we're taking a sample of 64 cups. We want to see if that sample represents the population. We want to build a confidence interval that will contain our actual population mean. Will it? It should at 95%, but there's occasions where it might not. We might get a figure here, but we're building at 95% confidence. So we're going to be pretty sure that the filling station is whatever numbers we get, it represents the population, meaning every single cup that's coming off the line. Using the confidence interval then is the process filling the cups to the desired amount. The morning cups had a sample mean of 4.015 ounces. Okay, so that's the information that we're going to be using along with this standard deviation. And again, I would go ahead and put all those in because we know, and here's the actual, I'm going to bring this up because this is the actual formula here that we're filling in. So our sample mean is, I think I filled that in wrong. It's 4.15, sorry. 4.015 ounces is our X bar, our sample mean. That was from the 64 cups that were pulled in the morning. Plus or minus 1.96, which represents our 95% confidence interval, times, I could put parentheses around to say times, our population standard deviation, 0.04 ounces, divided by the square root of our sample size, which is 64. Okay, and that makes it nice. I think 8 is 64, so that's 8. So it'd be 0.04 divided by 8. And now if I go ahead and do this formula, if I go ahead and I figure this all the way out, it is equal to 4.015, and then it's really this side of the equation here that, I'm sorry, let me just do something because I want to, it's really, oh, you just can't see that, can you? Until I format it. We don't want any fill in there. It's really this side of the equation, right, that we're going to do the calculation. We're going to do this first, this part in parentheses, multiply it by 1.96, and then we're going to add it and subtract it to this sample mean of 4.015. Okay, so when I do this side of the equation here, it comes out to 0.0098. We want to make sure we represent that accurately because when we're doing confidence intervals, it's really going to be tight. So we want to make sure we take it out. If it's 4 or 5 decimal places, take it out. So this part of the equation comes out to 0.0098. And I would highly recommend for you to just do this even and make sure you come up with that number. You know, do the 0.04 divided by 8 times 1.96, 0.0098. Then we take that number and add it and subtract it to that sample mean. So 4.015 plus 0.0098 is that, and 4.015 minus 0.0098 is that. And I should have done that one. If I want to put that one over here so it makes a little more sense. Okay, so our confidence interval then is 0.0052 to 4.0052 to 4.0248. Okay, let me make that a little, because that's our answer. That's what we're going to report to our boss. So the question is then, is the machine filling it to our required 4 ounces? We have 4-ounce plastic cups. Is it filling it to those 4 ounces? Yes, it is, because this one, the low part of our range, the part that's down here, is 4.005, and the high range is 4.0248. So if those numbers were put, you know, where they should be on the graph here, we know that the population mean is going to fall somewhere in between this. Let me say that again. We're 95% sure that the population mean, all of the cups that we have coming off the line, are going to fall between these numbers. The lowest end of this number is still above the 4 ounces that we're required to have in the cups, okay? It's not quite 4.01, right? So, you know, maybe we're filling in a little less than this, but really the question asked, are we filling it to at least the 4 ounces that the customer is getting? And yes, we're 95% confident that we're at least filling into that 4 ounces that the customer is required, because our confidence level dictates that, right? So I can go to my boss and I can say, yes, the machine is filling the plastic cups with peaches and gel at least to the 4 ounces, if not slightly over the 4 ounces. We don't need to shut the machine down. We don't need to do the maintenance. We don't need to clean the machine. It's doing its job. I would say we have to keep an eye on it because it's not quite living up to this 4.01 that we have. It's slightly below that. So it might be something we want to keep an eye on. But as of right now, we don't need to shut the machine down because we're 95% confidence it's doing at least 4 ounces in the containers. Okay, now the other part of that too is, the actual population mean could be here, very close to the 4.025, which means we might be filling a little more than we should, so we want to be careful. Or it could be very close here to the 4.005, which means we may be inching down towards under 4 ounces of peaches, and then the customer's going to start getting mad, and we don't want to have that happen. So, but for right now, we could assume that the population mean is somewhere between those 2 points, and that's the way we would report those results. Okay, so that's an example of a confidence interval when we know the population standard deviation. Okay, we're still pulling a sample because we don't want to ruin all of our peaches in gel to know something. So we're pulling a sample. In this case, it was 64. We're using that sample mean as kind of our starting point. And then that confidence interval and error figure combined will give us some kind of interval we could work within. From that data, we could make inferences then about the entire population. Every single cup that is coming off the line for that day, we could say is going to fall between these two mean averages, and then know whether or not we're operating within a certain interval, within a certain capacity that's required of the process. Okay, so that's this. The next video we do will be on if we don't know the population standard deviation, and we have to use the standard deviation from the actual sample that we get. And you could assume there's going to be a little more error involved in there. So, but it's the same idea. We're still constructing an interval and still trying to make inferences about the population.